Welcome to another video of Optatube. We're going to start with a question about something you use every single day, but probably don't think about much: the electricity powering your life.
I mean, really, have you? It's not random. There's this huge invisible process happening constantly to make sure the lights stay on. So how did the people running the grid decide who gets to generate power and who has to wait?
Well, it really all boils down to one simple, critical factor: cost. The whole goal is to find the absolute cheapest electricity available at any given second. And the mathematical tools they use to figure this out, they're called cost curves.
So in this explainer, we're going to pull back the curtain on the 4 key models they use to calculate these costs. We'll start simple, with linear and quadratic models, then get more realistic with cubic and stepwise functions. After that, we'll actually decode what all the math means, and wrap up by figuring out how to choose the right model for the right job.
All right, let's ease into this by starting in a kind of perfect simplified world. We're going to look at the two most basic models out there, the linear and the quadratic.
First up is the linear cost function. This is, by far, the most straightforward way to think about it. Just imagine a power plant, where for every extra megawatt you want, the price goes up by the exact same amount. It's a perfect, predictable, straight line.
And the formula? It's beautifully simple. The total cost, which is C, equals A. That's your fixed cost just to keep the plant running, plus B, the variable cost, times P, the amount of power you're making. Super clean, super direct.
So when would you actually use this? Well, it's perfect for teaching the basics or for modeling really small things, like a backup diesel generator. Why? Because it's super easy to understand and crazy fast to calculate. The big downside, though, is that it's just not realistic for most big power plants, mainly because it totally ignores that generators lose efficiency.
So, to get a little closer to reality, we bring in the quadratic model. This one gets a key detail right. Most power plants actually become less efficient the harder you push them. So the cost doesn't just go up in a straight line, it starts to curve upwards, getting steeper and steeper.
Now look at the formula. All we did was add one little term, C times the power squared. But that tiny addition, it changes everything. It takes our straight line and bends it into a curve, a parabola. That upward curve is the math showing us the plant struggling and becoming less efficient as it cranks out more power.
This model is the real workhorse for most big thermal plants. Coal, natural gas, nuclear. It's way more realistic, and because of its smooth curve, it's a dream for optimizers because it gives them one clear, cheapest answer. It's not perfect, though. It still ignores some pretty big things, like the huge costs of just starting up or shutting down a giant plant.
Okay, let's leave the ideal world behind and step into the messy, complicated real one. Now we're going to explore the cubic and stepwise models, which bring in even more real-world grit.
This brings us to the cubic function. This is where things get really detailed. Think about an old, aging power plant being pushed to its absolute breaking point. At those super high outputs, costs don't just curve up. They can suddenly skyrocket because of all the stress and strain on the equipment. This model is built to capture that dramatic spike.
And you can see the complexity growing in the formula. We've just tacked on one more term, D times the power times cubed. That's the part of the equation that models those extreme cost jumps when a generator is being pushed way too hard.
Now, this model is incredibly flexible. It can match up with real-world data with amazing accuracy. But that flexibility is kind of a double-edged sword. The curve can get so complex that it's no longer convex, which is a fancy way of saying it might have multiple low points. That makes finding the one true cheapest option a whole lot harder for the grid operators.
And finally, we get to the model that looks the most like how power is actually bought and sold in a competitive market. It's called the stepwise function. See, in the real world, power plant owners don't offer their electricity along a smooth curve. They sell it in chunks or blocks.
So instead of a curve, you should be picturing a staircase. A generator owner might say, okay, I'll sell you the first 50 megawatts for 20 euros each, but if you want the next 50 megawatts, that'll be 25 euros. Each step on this graph represents one of those blocks of power for sale at a set price. The great thing about this is that it's almost exactly how producers bid into the market, so it's incredibly realistic. But what's the catch? Well, all those sharp jumps between the steps make the optimization math way, way harder to solve than with a nice, smooth curve.
Understanding these models is absolutely key to power system analysis,
And hey, if you are interested in the energy market and power system modeling, or you want updates and insights about the global energy market, you should definitely follow the Optatube YouTube channel. Okay, now that we've seen the models, let's actually figure out what all those letters in the formulas really mean.
Those letters, the A, B, C, and D, they aren't just abstract math. Each one represents a very real physical cost. A is your fixed cost, the price of just keeping the doors open, even if you make zero power. B is the straightforward cost of the fuel you burn. C represents the price you pay for inefficiency as you ramp up. And D, that's the emergency cost of pushing old gear to its breaking point.
So now that we have this whole toolkit, let's put it all together and figure out how you'd pick the right model for the right situation.
Think of this table as your ultimate cheat sheet. It lays everything out side by side. You've got the simple and fast linear model on one end and the super realistic but complicated stepwise model on the other. Which one you choose really depends on what you're trying to do. Are you optimizing for speed, simplicity, or are you trying to get as close to the real-world market as possible?
Picking the right model isn't just an academic exercise. It's absolutely crucial for keeping our power grid stable and affordable for everyone. But it leaves us with a really big question for the future. You see, all these models were designed for traditional power plants. So, as our grid gets filled up with more and more solar and wind, which have zero fuel cost but are totally unpredictable, how are these fundamental cost models going to have to change to handle this new reality and, keep our lights on? That's the huge challenge facing the next generation of power system engineers.